see. Excellent stream health, nice. So here we go. Hello stream, hello world. Hello, hello. Back at it again. So yeah, welcome. So the plan for today is I am going to, I'll just review. So I solved about 10 of these problems while I was working, in between, sort of issues and things that grab my attention. And I'm just going to review them quickly here, just so that way, like, anybody who's been paying attention, we can sort of stay on the same page. Not going to go into detail on like how I solved them initially, and then what the better solutions would be. I'll just show you the better solutions as I recall them, explain them. And yeah, so we'll go through this. We'll try to go through the first 10 problems. It's more like 15 problems. It's a bunch of problems. We'll go through as many problems as we can until we're getting to problems that I haven't seen yet, and then we'll sort of do them naturally. You could watch me as I do them. So, write a function which separates items of the sequence of an arbitrary value. This is kind of cool. So what you do here is you can take repeat. So you're going to use an anonymous function. 2 arguments, right? This first argument is going to be what you repeat, and not repeat. Sorry, I'm giving it away. We'll talk about repeat in a second. The portion that you not join with, but the portion that the separator. There we go. Yeah. So the first argument will be the separator. The second argument is going to be the collection that you're going to place the separator in between. And what you can do is you can say repeat of this separator, and then you can take your collection and you can interleave. And this is a pretty cool function, but what the interleave does is it's like a zipper. It'll take one of one element and the next of the next element, one element, the next element, and it'll kind of all the way across. And what you can do is then, once you've got this interleave and you repeat, if you put the interleave, if you put the interleave first, you can use rest of this, and that ought to give you what you're looking for. Or you can do it the other way around and say but last, and you can put this repeating portion on the other side. And what will happen is, so the rest will drop the first element, and also this but last will drop the last element. And that's also the same solution. It's pretty neat. So we're not going to go into just destructuring. We're going to go to the problem list, and we'll go to number 41. Excuse me. Do these have? Uh-oh. These don't have... Nothing but the truth. I want to go by time. Oh no. Time solved. Shucks. 41 we want to see. Do these not have the... Come on, man. Maybe we can do it this way. Title. I don't think so. I think... No, it doesn't say. It doesn't say... Oh, no. What about 41? Is this it? Oh no, you're going to see the solutions. Okay. I'll just explain them then. Okay, so it looks like I can search by the number to find what I'm looking for, but alright. So okay, drop every nth item. So write a function that drops every nth item from a sequence. So 1, 2, 3, 4, 5, 6, 7, 8. Every third item means you're going to lose 3 and 6. So 1, 2, 4, 5, 7, 8. Here you're going to lose C, no, second item, you lose B and D and F. So you get ACE. Right, and then here you get 1, 2, 3, 4, 5, 6. You're going to lose 4. 1, 2, 3, 5, 6. And so each of these, where this comes from, the solution, so what you do is you partition, this is kind of neat, so you partition, which is a function that basically is going to take your collection, and it'll take a portion of the collection as a sequence, and it'll do that repeatedly, and it'll step through your sequence to create this portion. So as an example, if the step is 1, and you say, okay, give me 5, partition of 5 elements, it'll give you the first 5 elements, the next 5, the next 5, the next 5, the next 5, but the first 5 starting at the first index, the next 5 starting at the second index, etc., etc. So you would get, as an example, if you had like 10 elements, your sequence would be as the first set of 5, the next set of 5, the next set of 5, the next set of 5. It would be 10 times. So what you do here, in order to get end at the end, if you have specified a pad, it's called padding, then you'll take whatever elements are left over at the end, and you'll fill that sequence to get, for example, if you're using 5 elements, you'll fill that with the pad. If you use nil as the pad, then that sequence obviously is just those elements, leftover elements. If you don't use a pad, then all those elements are truncated, so they're just dropped entirely. So you can use this partition to do something kind of neat, which is basically break this up into pieces of whatever this value is, so 3. So you get 1, 2, 3, 4, 5, 6, and then 7 and 8 would be the leftovers. All right, you partition using this function, and you get this sequence of sequences, and then you simply so then what you do, but what you can do with this partition is also, if you modify the step just the right way, then you will skip. You can skip elements. So in our instance, what we want to do is we want to take the first 2 elements and then take the step to be at 3, right? So we get the first 2 elements, and not the step at 3, but the step is 3. So then you jump 3 elements to 4 and take the next 2, and then jump from 4 3 elements to 7 and take the next 2. And so you end up with a sequence of sequences where the sequences are of size 2, and they'll be exactly 1, 2, 4, 5, and 7, and 8, and 7, 8. Then you can concatenate all of those sequences to get the full sequence, and that gives you what you're after. So that's kind of neat. It's useful. Let's go to 42. Explain that. 42. Factorial fun. Now this one is interesting. I originally did something kind of funky, but the more concise answer looks like this. So what you do is, and you even probably want to modify this to use a couple things to say. So this will make your function it'll use big integers rather than sort of 64-bit or 32-bit integers, which makes it slower to operate, but it allows you to use much larger numbers. In fact, arbitrary precision numbers is really what you'll end up using. And then you also, so what this does is you say, okay, give me a range from 1 to, including 1 up to the number that we're interested in and including that number. This increments the value, and then this range is actually, it's exclusive, so it'll increment, it would normally drop this value that you're interested in, but because you know you've incremented it, it drops the incremented value, so you end up including the value you want. And then you apply, what this does is this says, okay, well this is a sequence of values. We're going to treat this sequence of values as if they were all just arguments to this function. That's what the apply does. And then obviously this multiplication, it works on an arbitrary number of, it's variadic, meaning it's an arbitrary number of arguments, so it'll just multiply all the arguments together, the ones that you give it. And there you go, that's what factorial is. It's just 1, 2, 3, all the way up to n, multiplying all that across. So there you go. Pretty simple, pretty elegant, I think. Straightforward. I appreciate that. 43. I don't need to, okay, reverse interleave. All right, you can see the answer again. So this is interesting. So you saw interleave, which goes from these before it was 2 sequences. I think you can interleave more than 2 sequences, by the way, but we were just doing 2. Or no, we were interposing, excuse me. Yeah, we were interposing, which is a little different than interleaving, but we used interleave. I think you use interleave with more than one collection, but this reverses the interleave, meaning you get a sequence of values and a certain number of collections you're going to reverse interleave this to, and then you are returned a sequence of these different sequences. And the way that this works is really cool. So what you do is you partition, same partition function that we were describing earlier, you partition on this sequence using this value, right? And also drop at the end. You also don't keep any extras here. You drop the other stuff. So you just lose it. So you drop, but you truncate. So what you do first is you partition into these different sequences, right? Exactly using this size of 2. And what this is going to do is oh, wait a minute, is that right? Hold on a second. Let me tinker with this a little bit. Actually, I thought that yeah, let's do this partition with two. Does that do what I think it does? One, two, three, four, five, six. Really? If we did 2, step 1. Excuse me. Yeah, okay, that's interesting. So the step is by default equal to the amount that you're partitioning if you don't include the step. If you do include the step, you can do something interesting like this, where you end up with, this is what I was trying to describe before, 1, 2, 2, 3, 3, 4, 4, 5, and 5, 6, where they're actually intersecting partition boundaries, overlapping partitions, overlapping partition pieces, we'll call them. Where the reason why that's interesting is that the mathematical definition of a partition actually implies that they do not overlap the pieces. So this is a particularly interesting function. It doesn't follow its mathematical what do they call that, cousin so closely. It's kind of cool. So all right, anyway, yeah, I just wanted to clarify that. Looks like, because I was like, wait a minute, it doesn't look right. But anyway, so you see how you get this sequence of partitions, or sequence of sequences when you partition. What we want to do is take this sequence of sequences, and now what we're going to do is we're going to apply a map of the list function across these values. Now this is really going to look, this takes some explaining. So what map does is it takes a whole bunch of collections, now variadic on collections, and it'll take the sequence of all the first elements of each collection, and then it'll apply a function to that sequence. Then it'll take the second element from each of those collections as a sequence and applies a function to that sequence, where the arguments to the function or the values in that sequence. So we'll do the first elements, the second elements, the third elements, etc. So what that means is that in our partition here, it'll take 1, 3, and 5 as the arguments to the function that you're mapping, and then it'll use 2, 4, and 6 as the arguments. So all you've got to do is actually use a list function to just create a list of all these elements. And so now you'll end up with a list of 1, 3, 5 and a list of 2, 4, 6, which is exactly what we want. And the only tricky part here is that, okay, so you say you just map the list over the result of this partition. Well, this map function takes a variadic number of collections. It doesn't take a sequence of collections, which means that you just need to throw in an apply at the front to tell the compiler that this is actually going to be a sequence that's going to be interpreted as a bunch of variadic arguments, and then you're going to use those variadic arguments, filter that into this map list, which is the function is a map, and then the function that you're using with map is list. So it ends up working out exactly as desired, but it's pretty wild. I mean, it's pretty, like, there's kind of a lot of things going on here, and it makes it very concise, very terse, and very clear. Yeah, really cool, really cool. But that's how you can reverse interleave, is you can apply apply your map using the list function to a partition on exactly the number of sequences that you're looking for. So yeah, I really appreciate that. I thought it was really cool. The one that I ended up writing was actually had more of a used like a hash map kind of thing. Not really a hash map, but used something else that wasn't so impressive. It was not nearly as impressive and interesting and concise and so on and so forth. So let's go to 44 now. Rotate sequence. Now this is kind of cool. Yeah, you already see the answer. This, I kind of ripped this one directly from someone else because it was just so good how they did it. But the basic idea is you can. So what this says is write a function which can rotate a sequence in either direction. So rotating in one direction is kind of straightforward. All you've got to do is just take, the first half of the sequence and put it on the back of the other half of the sequence, and this would, not half, but however many elements deep you are, that's how many elements you take from the front, and that's how many, and then whatever's left over you take from the back, and then you just swap those two, and that's how you rotate. Pretty straightforward. So that's going to be a concatenation of one piece with another piece. Now the part that's interesting is that you could say, okay, well, there's two more things that are interesting here. One is you can use negative values, right? So rotate in the other direction, and which presents kind of an issue because you might say, like, well, that's actually just equivalent to taking the whole number of things you're working with and adding it to that number, and whatever that positive number is, then it's the same rotation. And that's kind of the only way to really interpret it, to understand it. And then you could say, okay, well, then I guess it's kind of straightforward. We just got to replace this value that we're interested in with, if it's negative, add this count to it. A couple ways to view that is to actually, you already have the answer here, but you could add count to everything and then take modulo of the count, right? So if it's positive, and you'll end up adding this 5, and then when you take modulo 5, you end up back at the positive number. If it's negative, then you end up adding this value, and the modulo doesn't do anything, and you're where you should be, where you just have one single addition. That will give you. Now, what's interesting about that is it's actually wrong. So I actually had it wrong the first time around. The reason why it's wrong is because you can have, technically your rotation could have an infinite number. It could be infinitely positive or infinitely negative. So actually, you do need to take modulo. It wouldn't actually be wrong. Actually, now I'm thinking about it. It wouldn't actually be wrong. And the reason is the modulo function, how it works in Clojure, is that you can actually take a negative value. I think you will get the sign of your modulo will be equal to the sign of what you're taking modulo, if that makes sense. I think that's how that works. So if you had like an incredibly negative value, you could still take the modulo and you'll get a positive number to represent. That would represent, adding whatever that modular number is. I guess it's, like if you're taking like x mod 5, you add 5 to x repeatedly until you have something that's between 0 and 4 inclusive. So yeah, so actually you don't need to add this count and then take the modular value of it, which actually wouldn't even be correct anyway. What you can do is just take the modular value directly, and this will give you something positive. And so we label that k, take this mod, the input, and modulo the size of the vector that we're interested in. And then you can concatenate these two pieces. You can find these two pieces, and the way that works is drop k, take k. Drop k means you're going to drop. Now this is also interesting, is because you might say like, well, let me get the last 3 values and let me get the first 2 values, which is what I did initially. And the last 3 values means it's the last values of, you'd have like take and take last, and then this would be 5 minus 2, it would have to be, or 5 minus, actually no, negative 2 would be these last 2. So it'd be 5 minus 3, in this case it's 5 minus 2. And yeah, 5 minus 2. And the problem with that is it's not very concise. Whereas if you drop the first 2 elements, right, and you get this piece, and then you take the first 2 elements and get this piece, then it's very clear that you can combine the one for which you dropped comes first, and the one for which you took comes last. And so it's very, very, very clear, very simple. And there's not all this extra garbage in between where you're defining this, so how much you're supposed to take of the last amount, where you have to sort of take the difference between this count and k. Not that it's that much more unclean, but this is like a very clean approach to it. So yeah, I appreciated this solution. Copied it. Had something very similar, but yeah. So we went over that. Let's go 45. Intro to iterate. This is kind of neat. This we don't really need to go over. You produce an infinite lazy sequence. So this is what this is going to do, is take f of f of f of f of f with a starting point. So this first function, so it'll initially take x, which is 1. Then it'll take f of x, which is add 3 to 1, which is 4. And then this next iteration will be add 3 to 4, which is 7. Then you'll be add 3 to 7, which is 10. Then add 3 to 10, which is 13. And that'll give you the first 5 iterations here. So that's what it looks like. Kind of neat. Let's go to 46. Flipping out. So this is kind of cool. This is a very interesting question. This is sort of the first, I guess like one of the first ways to understand what a higher order function does. So a higher order function takes as an argument a function and then returns another function. It's more or less what it does. And it might take other arguments as well, but basically higher order functions return functions. And so as an example, like a very concise example, is if you could imagine a function that takes as arguments x, y, and z, that's some function f, and what you want to do is return, given that f, return g that does the same thing that f does, except its arguments are in a reversed order, so it would take zyx rather than xyz as its arguments. which is exactly what we do in this problem, as we show how can we define a function that will, given a function, returns the same function but using arguments reversed, using its arguments in reverse order, and or accepting the same arguments in reversed order. So that's sort of a simple, very simple higher order function. That's what we do here. And here you go. We're going to have a little bit of some checking in here. So we've got this function that takes an argument f, anonymous function, checks if this f is a function before we do anything else, because obviously this won't make very much sense. Might actually even crash the program if this is not a function. I think it will, probably will. And then we say, okay, we're going to return a function, anonymous function, and that's going to take as input these arguments. It's going to take arbitrary arguments, right? This function, and we're going to apply, and this is a sequence. Obviously, it's a variadic number of arguments. We're going to apply f to the reverse of those arguments. So what you're going to get, given f, you're going to return this function, and what this does is this has an arbitrary number of arguments, but what you're going to do is reverse that sequence and then use apply to sort of spread those arguments out as if they were not a single sequence, but just a series of different arguments that a series of different arguments that you want to use in your function. And then we're going to apply f. Then we're going to call f with all those arguments, but obviously they're in reverse order. So there you go. That's exactly what you wanted. You wanted g in which takes the arguments in reverse, and that's what this function does that you return. So that's it. Very, very straightforward. And there you go. And then what they're showing here is, given nth, and a bunch of different functions that you could have two arguments to. This is any number of arguments, obviously, but it could be two arguments or whatever. You could easily write this through two arguments. But I think it's better to do it for all arguments, right? It's for sort of for the general case, more general case, so to speak, or the general case. All right, let's go to 47. Contain yourself. Contains function checks if a key is present in a given collection. Okay, yeah, this is kind of straightforward. Although this is interesting. This will actually tell you, if you do this on an array, you'll just check if the size of these. It really just checks for like an index into the array. So 4 exists as an index into the array. I think 0, 1, 2, 3, 4, but 5 doesn't here. Whereas this will check directly into the hash. This is a set, rather. Yeah, this is a set. So yeah, 4 is in the set. Here this is a key in the hash set, hash map, which the key exists, and then here it'll also check. Oh no, here, right, not will be true, because when you check 1, 2, 3, 1, 2, yeah, when you check 4 in here, even though the value 4 is there, index of 4 does not exist here, right? 1, 2, 3 doesn't. So there you go. So this would be false, and then not will make it true. Not too much to go over there. So now we have intro to sum. Let's get a little bit closer to where I stopped last time. We'll just check how we're doing here. Okay. So the sum function takes a predicate function and a collection, and it returns the first logical true value of predicate x, where x is an item in the collection. So what this is going to do is it's going to operate over this collection and execute this predicate on each value of the collection. And the first time that it's true, it'll return the value that it operated on, right? Which is kind of interesting. So it'll return this return value. Yeah. So assuming that this predicate is true, when this predicate is true, whatever is returned from this predicate is what ends up being returned by sum. which is kind of special, kind of important, and that's why you get 6 here, down here. You'll see. So both of these end up giving you 6. So 5 isn't here, you get false. 6 is here, you get true, and you end up returning the 6 itself because it actually is a value that is returned by when you check 6 against this set. Now if you do that here, right, if you just did even %, even would return true or false. So if you did even, you would stop at 6, but you would return true. This value would end up being true. If you use when, what when does is it says if this is true, execute this body here, which means, but this is effectively just returning 6 in this case, or returning the value. So when the thing is even, return it. When you use that with sum, you end up with a true because this predicate returns something, and then you actually sum ends up returning whatever that is. So kind of a little more nuanced than you would think, I guess, but interesting. So just that sum, this is much more of like the sort of mathematical there exists in a set. Yeah, it's just that there is something in that set that satisfies this predicate, and we'll give you that item. So that's sort of where's this sum? Just something that satisfies this predicate. So pretty interesting. Haven't really used that much yet, but it's there. It exists. Let's try split a sequence. So this one, very concise, kind of interesting. We'll explain what they're asking for, what this does. Write a function which will split a sequence into 2 parts. So at some point, you're going to break the sequence into 2 pieces. And it looks like a vector of these 2. So the simplest way to do this is to use this juxt take drop. Really, this is a concatenation of a take and a drop of however many values, just like what we did for the rotation. It's very similar to the rotation, except you can make this even more concise, because what you want to do is put all these values into their own sequences, and then put those 2 sequences inside of a list, right? And juxt, what that does almost exactly that. What it does is it takes functions, creates a new function out of these functions, and what that function will do is it'll apply each of these functions, given whatever the arguments are, and then it'll create an array of those results. So if this is sort of F1 and F2, you would have F1 of this whole thing, and then F2 of this whole thing, and those 2 results end up in an array that you end up sort of. So if you had more things here, you'd end up with more resulting elements in that array of arrays. Or ends up being an array of arrays, but ends up resulting elements in that array. So you end up with exactly what you want, which is kind of wild, kind of cool. You end up with taking 3 elements, and it's all of the arguments, right? So you don't really need to specify much. Like all you need to do is just specify that this is you're calling this function to generate. This is a function itself, and so you use this function. The result of calling this juxt on take drop creates a function, and then you're actually going to use that function here with these arguments. Yeah, so the argument's 3, and then you just end up taking the first 3 elements and then dropping the first 3 elements, and then those get both pushed into the array. And so if we run that, there you go. Works out nicely. Pretty cool. Very concise. Very concise. Let's go to 50. Split by type. This is like kind of broken. Yeah, I mean you can tell. So we'll read it and we'll describe what's going on here. This also has a certain but relationship to the certain we'll call it relationship to the the reverse interleave function that we looked at earlier, because the reverse interleave can be done with a like a hash map, and this can be done with a hash map. Both of those in a similar way. But what you end up with is, okay, so write a function which takes a sequence consisting of items with different types and split them into a set of homogeneous subsequences. The internal order of each subsequence should be maintained, but the subsequences themselves can return in any order. This is why set is used in the test case. So what they're saying is, take all from your vector, your collection. Take the subsequences that have the same type, so like 1, 2, 3, see, and A, B, and C, right? These are all keys, and create sequences of those, but maintain the order within those sequences. So 1, 2, 3 should look like 1, 2, 3, and then ABC should look like ABC, and not like CBA or 3, 2, 1 or anything like that. And then return that sequence of sequences. But the subsequence within that sequence could be in any order. So this 1, 2, 3 could come before ABC or vice versa, right? Doesn't matter. And you can use set on the result to actually match, because a set imposes an order on your results. So it'll be consistent across executions. So what you can do is you can use a kind of hash map to do this. And what I did initially was use a hash map, and each element will be hashed to a key, that key being the type of that element. And each time you hash, if there's nothing there initially, then you're going to hash it. You're going to conjoin that element to a vector, a fresh vector. But if there is a vector already there, then you just add it to the end of that vector, and then you get a whole bunch of these vectors that are basically all the types that you've come across when you sort of span from left to right, iterate from left to right over the input collection. Then you can take the values of that hash map, which is just all of these subsequences that you're interested in, and just return that as a sequence. And you're done. That's it. That's the way I did it. I also applied a set to that, but you don't need to apply a set to that. So I used a simple reduction to do that with like an anonymous function, which basically did something akin to like a frequency map type of deal. Then I learned after I submitted, I learned that you can use a group by, which almost does exactly the same thing. Effectively does the same thing. You just have to provide the predicate that you create this basically creates the key given an element. So you group by type in this instance. This is very, very concise. Like I said, extremely clear what this does, what this means. So you group by type, and then you get the values of these groupings. So this creates a map, just like I did it manually. And then they get the vals, and then you return exactly what I was describing before. So the couple things here, though, this ends up being an anonymous function. This is a single input argument to that anonymous function, and then this is a threading macro, which will put this at the end of this, so this function gets called on this with this single argument, and then the result of that is what gets called here as a single argument to vals, and this greater than means it's all the way to the right of the function that you're using. So kind of neat, very concise, really like that. I'm kind of looking forward to programming with Clojure, because it's just super, let's go to 51, so it's super semantically enjoyable. So I think I said that I got through about 10 problems or so. I was around 40 we started at, so now we're at 51. So here we go, destructuring. Now I got kind of stuck on this when I was looking at it. Took us some time to review all of that, but we got there. Let me see how we're doing with our, how's the stream doing? It's, yeah, stream health. We're here. Been here for 40 minutes so far. Okay, wow, it took 40 minutes to go through all that. Yeah, I guess 10 problems, you spend 4 minutes each. It's pretty, yeah, I guess so. Okay, so advanced destructuring. Here's an example of some more sophisticated destructuring. Right, so, okay, what we want to do is get this at the end here. We can get rid of all this stuff too also. We don't need all this. Get rid of all these things. We want the result of this to match this guy. So let's print this. I stretch my hands to you. So I'm curious what this will give us. You destructure this thing. Stretch my hands to you. Oh, that's exactly what we want. Oh, I know what I did wrong. Okay, I was gonna say, so when I did this initially, so I'll explain what's going on here in a moment. But when I did this initially, I know what I did wrong. Yeah, all right. So I'll explain. Allow me to explain. Allow me to explain. So what happens here, the way destructuring works, so you have what's called a binding, and there's within this binding there are pairs of values. So it's bindings will have an even number of arguments or parameters, more like even number of things. So it's got this special syntax instead of open and closing bracket opening and closing parentheses, you've got brackets like the beginning of a function, but it's a little bit different. And what this is going to do is going to take a bunch of variables and it's going to assign to those variables something from this expression. Now with simple destructuring, you might, or not simple, but a simpler form of destructuring, you may just have like a single variable a here, might look like this. So you might have something like just a, and then what this would look like is a is just whatever this is, right? So I'll show you what this looks like. Right, it's just 1, 2, 3, 4, 5, a sequence 1, 2, 3, 4, 5. But when you want to use destructuring, what you can do is say, okay, I'm going to assign to each of these variables from this expression. And in this instance, we could use a collection. And so this will take the first element in the collection, the second element in the collection. This will be all the other elements, the rest of the elements from the collection. And then this as D will take this entire thing and create a sequence out of this whole thing, right? So this will be a sequence of just what's left over. So in this case, this would be 3, 4, 5, and D is going to be the sequence including everything, which would be 1, 2, 3, 4, 5. And then it'll say, okay, you're going to also have A, B, C, and D. And now when you return here, what this is going to do is it's going to give you the first element of the sequence is A, whatever A was here, first element here, B is second element here, C is all of the other elements that was here, and then D is going to be all of these concatenated, all these values concatenated, and you can see it, and then this return is obviously a vector of these four things, which is exactly what we wanted. We wanted a vector that had first element 1, first element 2, right? First element, Then the next element is a vector of 3, 4, and 5, which is the rest of this, right? And finally, the final value is the vector of everything, which is exactly D. So, pretty interesting question. They kind of covered a lot of stuff here in one shot. Now, the one problem is that I was tempted to do this initially, and I'll show you what happens. And I got kind of stuck on this because it says it can't cast along to a function. Why does it say this? What does that mean? It kind of looks like gibberish at first. It means this 1 is a long value, which is a type of integer, right? And it can't be cast to a function because it looks like you're trying to call 1 as a function with these arguments. The compiler can't tell what you're trying to do here. So if you want a sequence, you have to unquote it. You have to quote it to avoid that problem, which means just add this here. Alternatively, you can use quote, and that should also work. Yeah, quote also tells the compiler not to try to execute this piece here as a function. It'll say, okay, just read this as a sequence of values. So that's how you can write literal sequences. Yeah, or sequences of literals or literal sequences, however you want to express it, phrase it. So there you go. So next, intro to destructuring. So let bindings and function parameter lists support destructuring. So we want to say 2, 4, A, B, C, D, E, 0, 1, 2, 3, 4. And we want, looks like 2 is C and 4 is E. So we probably want CE here. And let's see how this goes. Nice. Longest increasing subsequence. Hard. Okay, interesting. Given a vector of integers, find the longest consecutive subsequence of increasing numbers. If 2 subsequences have the same length, use the one that occurs first. An increasing subsequence must have a length of 2 or greater to qualify. Oh wow. Okay. Longest increasing subsequence. Wow. What I want to say is you can do a split by, I think it's called, or partition by, I want to say. Let's take a look at that. I think this is what we want. Yeah, each time f returns a new value. Okay, so what f is going to do is, so we're going to say partition by, so let's do it quote unquote in the lab first, where we take a look at this in the lab, in the editor first, and we'll say partition by, and we're going to use this value. Now the problem here is, no, that doesn't really do what we want. What I would like, yeah, so I can do this using a reduction, but I don't really like it, and I'll explain. But the reason why I can't really use the partition by the way I'd like to is that we need to compare the value that we're looking at with the previous value, which means we need to somehow maintain what the previous value is between executions, which is not a very functional thing to do. Right? It's sort of like quote unquote maintaining state, which I don't really want to do. So what we can do instead is we can use a reduction. So we'll have reduce, so we'll start with print line, and we want to reduce over with a function. Not sure what the function is going to be just yet. And the collection is going to be this guy. Use this first. can actually declare this to be a function too, which, okay. So what we want to do is we have this function, and then we're actually going to call it with this value as the collection you call it on. And that result we're going to print. Okay, great. So now what we're going to want to do is reduce. This function just takes a collection, right? It's this guy down here. And the function, how we're going to reduce is we're going to take, we have ret that we're going to, so we're going to use some destructuring here, right? We're going to use ret. We're going to have some value v that we're iterating through. X sometimes, yeah, like v is fine. And we also want to have previous value, right? And we're going to operate using that. And we want to reduce over this initial state, which is going to return two values. And what we're going to use is so the previous value is going to be v becomes the previous value. No, the initial value though should be nil, right? And we should have also a sequence, let's say. Just a sequence. Yeah, I think we can do this, right? Can we do that? Just sequence and Clojure. Seek and sequence are kind of interesting. So this converts a sequence, creates a sequence out of a collection. This, on the other hand, never mind. Okay. Never mind. We want an empty sequence. I think this might be one of the few ways to actually get an empty sequence. I don't know if this is like kosher, if I could do it this way, but anyway, what we want to do is return this vector of two values, start with this vector of two values, nil in an empty sequence. And what we're going to do is, as each value passes by, we're going to, now what does last do on a sequence? Last Clojure sequence, kind of time complexity. Digital business analyst, remote. Wow. Camel case. Interesting. Walgreens. Senior software engineer. Bloomberg. I should apply to this job, I think. Last, on a list or on a lazy sequence, it takes linear time, but on a vector set map string, maybe I do want to use a vector then. Yeah, okay, I guess we don't want a list. We'll just use a vector then. Okay, never mind. Never mind. All right, so what we're going to do is if this value, this new value v, is greater than the previous value, and we want to say previous is not nil. So if previous is not nil and this new value is greater than the previous value, is it strictly or just increasing? I think it's strictly increasing numbers. It's got to be increasing, not strictly increasing, right? If that's the case, then what we're going to go ahead and do is return. We're going to modify ret, and we're going to also return v as the new previous value, right? So the way this operates is this is going to call this function using the two values. What we return here from the last execution, really not return here, but or the initial value, and it'll use the next value in this collection. So there's sort of two moving pieces. This that we're updating, and each time we're going to update this, using a function and considering what's in this collection, the next value in this collection. So if we're not nil and we're also larger than the previous value, then what we're going to do to ret is take the last value of ret, which is going to be an array. So actually this is going to be an array of arrays. So we start initially with an empty array. Take that last value of ret, and we're going to vectors we can just push to the vector we just push to the back. Let's find out the vectors. Conj, pop, peak, count, associate. I think it's conjoin we want, probably. Conjoin we probably want. Yeah, just do conjoin. It's simple enough. Conjoin to this guy, v, and return that result. Yeah. Otherwise, we're actually going to go ahead and conjoin. So actually, I take that back. We're going to conjoin a new vector with v with ret and return that, and then you still have v. Also still return v. Right? If you're nil, then this is what you're gonna do. Otherwise, you're gonna get the last of the previous one. And or if you're not nil but you're not increasing anymore, you've now decreased. So this whole result, now this is going to give you a whole bunch of, well, it'll give you a vector of 2 elements if it compiles. Don't know how to create sequence from Java long. What happened? Don't know how to create sequence from Java long. Okay. Oh. Yeah, no, that's fine. Well, previous is nil, so this is nil. So you get the else. You say conjoin ret with. Now the problem with conjoin is that I think it gives me. Yeah, I think conjoin is not going to give me what I want here. I think I want concat. I think I want concat here. Because this is going to give you, right, okay. This adds things to the collection, not quite what we're looking for. It's really confusing, but like if we do, hold on, let's just comment this out for a minute. If we do conjoin this guy with this guy, This is maybe not exactly what you'd expect. Let me see. I'm very curious. Oh no, that is what I expect. It's exactly what I want. So never mind. This is exactly what I'm after. What's going on here? What is going on here? What's the issue? 55. Which line? 108. Be nice if it told me which spot. It doesn't tell me which line that this is occurring in. This is a runtime. No. Is this a runtime exception? Compiling. No, it's a compiler exception. So I did something funky here with my what? How to create a sequence from a long value? What do you mean? What do you mean? Ooh, excuse me. I don't know, is it these things? Does this matter? Just return the same state repeatedly. Do 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 do. So this is no problem, but apparently one of these is, I guess. Oh, you're kidding. Oh, no. What? Oh, I did this wrong. Wait a minute. That's the error here. Oh, I did something very wrong here. Is this, wait a minute. If you can join, it's supposed to be two things that can join. Oh, I see. Aha. All right. I did something very wrong here. Okay. So you got to associate with ret at the last position, which is count of ret decremented. You've got to associate this with this last of ret conjoined with v. I think that's what I got wrong here. Yeah, you got to return your vector of vectors appropriately. And then Right. Okay, how does this look? I think I don't know, did something funky. Oh, there we go. Okay, we back? Alright, so that wasn't great. Alright, well, as you can, okay. As you can see, we're looking at an interesting position here. I don't know why this is 40 to 140, but anyway. So, to return to what we were doing, sheesh. Okay, looks like we got it though. It's just hopefully my phone can last. Switch to a different network to stream on here. So let's see how this goes. So what we're going to want to do is take this function, and we're going to want to go even further and take another reduction on this, which is okay. So we have this function, right? So then what we're going to do is we're going to apply a filter of the size. So anything that's less than size 2, it doesn't count. And then we're going to take another filter, not another filter, another reduction, which is going to get the maximum count. Yeah. So we got 2 reductions. So we're going to use another function, threading macro, right? And we're going to take this function, leave it as it is, threading macro this value, which is going to be this thing. We're going to have this function. So we do this first, get all these sequences. Then we're going to have filter, it's going to be the count of this value is got to be greater than 2 or greater than 1. Right? And we also want to get another reduction, another reduce, which is going to use an anonymous function. And the starting point is nil, right? And we're going to say basically if I don't know, if takes two values. If the count, we're going to compare counts of these values. I was thinking you could do something with a map with these counts. Like you could map count, but you don't really want like, can you really use a minimum as a key? Not really. Like, can you provide a key to the minimum? I don't know. I think this is fine using reduction, except count is being used on both the arguments. And you compare the count. You say if this count is larger, or the second count is larger. Yeah, let's do the second count is larger than the first count. Then we want to return the second of these. Otherwise, you're going to return the first. And then we want to say also if this first, there's an and here, and it's not equal to nil. This what value not equal to nil? This first value. If this first value is not nil, and the second value is larger than it, then take the second value, otherwise return the first value. Actually, if it's not nil, you want to return the second value. Or yeah. If it is nil, you want to return the second value as well. I think the count of nil is just 0 anyway. I think this is fine. I don't think I actually need to worry about that. Yeah. So this is great. This is great. Fantastic. Fantastic. So this, I think, is the solution to our problem. Now, that took a very long time for me to program that. That took a very long time. I would not say that was concise at all. I think maybe I just need more practice, probably. Well, yeah, it won't compile. Something that complicated, it's not going to compile. Initially, definitely not. Never. Never. I had something before that was pretty good. Oh my goodness. Alrighty. I don't need this threading macro anymore. Whoa, what's going on with my phone, man? So first, I'll just make sure this thing works as intended. Which I think it does, right? I tried that already. Hopefully my phone can keep charging. Yeah, so this does work. And then, we gotta add the next piece or pieces, which looks like this. So that works. let's see if we filter. Oh, maybe that's because this has got to have, oh no, that's fine, that works. What if we do this? Shouldn't this work fine as well? What happens here? Oh, okay. I guess that doesn't execute this function. What? Excuse me? Wait a minute, what? Is this not, I thought, hello? 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 I am missing something. Oh, I am missing something. Oh, no, 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 no. No, no, no. Uh-oh. 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 What the heck is this? What the heck is this? What the heck is this? This don't make no sense, man. This don't make no sense. That's not right. Nope. What happens if I do this? Maybe that's the problem. I just don't know what I'm doing here with this. That does not make sense. Does not compute. If we do something like this, we say, okay, do this. No. What? What is going on? That doesn't make any sense. I am so confused. Hello? What do you mean? What? Holy smokes. No. No, 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 no. No. Hello? Hello? What is going on, man? Absolutely not. No. What? What? Oh no. Oh no. What the heck is happening? Alright, I guess I have to go look up what this threading macro does when you're using anonymous functions. That does not make sense. Something's not right here. Oh man. Okay. Thread last. I'm utterly confused. Last item in the first form. I am so confused. I am so confused. Jeez, man. Jeez. What? 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 That's okay. Alright. Alright. What is going on here? What in tarnation? What in the Sam Hill? Ah? Last item in the first form. So this is a function now. Can we call this function? Oh, that is so confusing. What is going on? What? What? What does this return? What do you mean? It's a macro. It's a macro. Okay. What does the macro do? We gotta know what this macro does. We're gonna pretty print it. Can we pretty print? How does that work exactly? Hold on. It's a way to do this. P-print. Yeah, we'll just p-print the macro expand of what does that look like? I think we need, can I do this? No. How do I don't remember how to macro expand exactly. Oh, form. Clojure pretty print. Macro expand. Okay, I got it. Clojure.pprint. What we want is something like this. I just filter of, I don't know, is it even? Right? Just that. What do we end up with here? Holy guacamole, man. Something is not right. What? Oh, I don't have pretty print. Oh my goodness, come on, man. Clojure pprint. Let's try it here. Require pprint. Come on, man. through even, macro expand. So what does this look like, this macro? This whole thing. Oh. Just a whole lot of hoopla, man. A whole lot of what in tarnation? What in tarnation? What does this expand to, man? What am I missing? What's wrong? What is wrong? Not to mention, this could be macroed as well. Just first reduce function. Well, not really. I guess you just, nah, that's fine. But definitely other pieces. Okay, maybe macro in first. Nah, not really. That's not really much of a benefit doing that. But what does this do? Oh. Does it do something here? This anonymous function? I get this feeling like it mangles this anonymous function somehow. Oh. Huh. Oh. That does something kind of interesting, huh? There's this if. Then there's this function. Isn't there reduce in there? Wait a minute. What happened? What happened to my reduce? What is going on? So maybe I cannot use this macro as I thought I could. Because what the heck is going on? I don't see a reduce anywhere in there. Alright, whatever, we don't need to use this macro. I'm super confused, but who knows? Would have been nice to use this macro though. Alright, whatever. Who knows what's happening? Jeez, man. We could use a let, I guess, but I don't want to use a let. Yeah, I suppose. Alright. Make things interesting here. Comment everything else out. Holy smokes. Why is it so complicated? I really don't know. Let's use a let. Put all this into a let. Okay. And inside this let, we have a couple things. Whew. Okay, we're going to have a function, and we're going to call this increasing sequence, and then this is going to be inside here. So we got this first, and we can do even another piece here, which is going to be reduce center, call it. These are all local anyway, so this really doesn't matter. And we can make this a lot simpler now. Just really make this simple, this function, right? This is, I think, a little bit cleaner. So this is our reduce center function. Reduce first, let's given this collection, this increasing sequence. And now we can try this here. Let's see how this goes. This has increasing sequence, and then these other pieces. Let's filter this reduction, second reduce. All right, how do we do? How did we do? No, come on, man. Just come on, man. Okay. It's like, what the heck? It's ridiculous. This is ridiculous. This is ridiculous. This is completely ridiculous. This is completely ridiculous. Okay. Okay. I bet it's just this reduce doesn't make a lot of sense. It's probably the only issue here. Let's try that. Yeah, that's the only issue. Why though? What's wrong? If this if is the issue? Oh. Yeah, what? What is the problem? Nice. That was it. Maybe, okay. Just the if, that was the problem. Try again. Try again. Oh. No kidding. That, so is, okay. Yeah, no, that's fine. Yeah, it makes a lot of sense. It's just, it was just this. That was the issue. It's just this. Please. Please, 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 please. And, Okay. Oh, of course. So this one does not work, I think. Just doesn't work. So who knows why. But this one I think does work. I don't really fully understand why either. I thought functional programming was going to be a lot better. I don't know, maybe it's because it's like pseudo imperative, but I don't know what's going on, man. This just isn't correct somehow. You know, I don't know. I really don't know. So none of his function. Maybe it's got something to do with this. Like maybe you just need one of these here. Yeah, that's it. Oh, that was it. Amazing. No kidding. Really? What? I just took a shot in the dark at that one. Wow. Okay. Yeah, that's insane. That's completely nuts. That's completely insane. What? What do you mean? What are you even talking about? What is... the heck is going on, man? Ah, yeah, like, of course. This makes total sense. Okay. X's, let's just say. X's. See how that goes. Oh. Hey. Fail. What? What? I guess it's not nil, it's... X's and O's, they haunt me. Oh, they want me. I guess it's, instead of nil, it's going to be the empty set. Oh my goodness, man. Hard problem. That's not that hard, though. It's just... I don't know, man. I don't even know anymore. I don't know what to think. My freaking head hurts. This is ridiculous. This is nuts. This is nuts. Alright. Looks like everybody else has got some crazy stuff going on as well. Loops and reductions and filters. Reductions. What does this do, reductions? Oh, look at this. What is that? The macro expand is function. What? Holy smokes. That's hysterical. Sort, set, flatten, map, function, apply, max key, count, conj, reverse, filter, F first, partition by first, map, function, partition, interleave. What is this? Conj, rest, last. And just a million of these at the end. Yeah, that... the heck am I looking at? Amazing. That's hysterical. I don't know how I feel about Lisp likes now I'm thinking about it. It's like, okay. I guess this is much more readable. I mean, this is only one, like, I know what this does. It's just, it's really funny. It looks funny. Reductions, what does that do? Clojure reductions. Oh. Oh, it's a real thing. It's real. Yes, sir. It's real. Oh my goodness. Yeah, so everybody's is looking real funky. Everybody's is looking real funky. Do all kinds of shenanigans here. Nobody's is particularly concise. Wow, look at that. Look at how many different ways this comes out. Wow. Jeez, man. Holy smoke, look at this. Some of this code is like, whoa. 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 I just like reduce. Reduce keeps things simple. Oh my goodness. Excuse me. This is imperative though. This isn't really what you want. What functional? This is like strictly, this is functional out the wazoo. It's functional like nobody's business. I don't know what's going on here. This is crazy. This is nuts. I mean, it's great, but it's like, what am I looking at? There's a lot going on here. It's a lot going on. You gotta take some time to really figure out what's going on. This is the most concise one here. Everything else is a mess. This is pretty good too. I like this one. I like these two. I'll highlight these two. Everyone else is like that. Everyone else's looks like mine. Same one twice. Wow. I like the one-liners, man. Appreciate the one, what do they call that? I appreciate the functional one-liners. It's pretty good. This is pretty good too. Alright, I'll probably look at these ones and then go to the next thing here. Oh, look at this guy down here. It's just wow. Okay. What does reductions do though? Do you know what that does? So lazy sequence of the intermediate values of the reduction as per reduce of collection by f, starting with init. Reductions 1 1 1 1 1 1 2 3 4. Reductions 1 2 3 1 3 6. Oh, just like reduce, except the calculations collected during the reduce. Cool. So interesting. So reductions is just like a reduce, but you get each piece as you go. Oh, okay. That's kind of cool. So we got reductions of, now what does this thing do? Oh, this is almost exactly what I did. So we filter for everything that has a count less than 1, or greater than everything that's filter for things that have count greater than 1, and reduce on the counts of these things, so you get the maximum, and your default is the empty. Oh yeah, oh wow, so this is really clever. So he did this. This piece of code does this here. Wow, very interesting. So how did he do that? So he says, reductions, conj, reduce function, there's 3, right? 3 values you reduce on. Well, how many things do you give reductions? How? This is an if. Last increment equals, return this or return this. And then you operate on, so this is the function, the reducing function. This is the initial value. This is the collection. Yeah, okay. Fair enough. What does this do? So I'm not sure if you need to have anything in here that's -2. Say, so the next value, if that's equal to the increment of the last value, so like -2 plus 1, if they're equal, so if increasing the last of what's being supplied, no, what you're currently looking at. Oh, I see. What does this do? Sorry, I need to like pull this out and look at it. Not big brain enough to. I think I know what this does, but this is. I think this works because this reduction, excuse me, at the end, you can do even more sort of intermediate sequences. Oh, that's very interesting. Although I think this gives you quadratic running time if you do it this way. I think I know what happens here. I think actually you don't want to use this approach because even though it's concise, it's extremely inefficient. Let's see what happens. It's also kind of why I don't really understand it. It's because, yeah, it's exactly what I thought it would do. It actually generates the sequences in between. So the maximum will still be correct, but you'll also have. No, it's not going to give you. No, it could give you quadratic. Yeah, it could give you quadratic time. Because you could have just if it's just a sequence that's going straight up, then what you end up doing is what do you call that? If you have a sequence that's going straight up, it's then it'll create an array with one value, array of arrays that have, the first array has one value, next array has 2, next array has 3, 4, 5, all the way up to n. And that gives you a quadratic number of elements that your algorithm's got to touch, or at least generate. Add to each of those sets, we'll say. Yeah, because I think you can't get away from that. Even if you're dealing with immutable sets, I think you still can't get away from creating this structure, this vector of all these things in there. I could be wrong about that. I'm really curious though, the time complexity of this reductions, the way that this has been written, the way that what I wrote is a lot more efficient, I believe. Although I could be wrong. Maybe this is also similarly inefficient because you're creating this ret in between every time. I don't think so. Because each time you associate, like, it just modifies this data structure. It doesn't generate a new data structure, and even though you return this, it's more like a reference to the data structure, which I don't think is that inefficient. I think it's okay. But that you could argue the same thing, that this is actually just a bunch of references to that data structure that's growing. These are what do they call that? Has a name. What do they call that? It's persistent vectors. Yeah, this could just be references to persistent vectors, in which case this is fine. I'm going to assume reductions is okay. We'll find out in practice, though. We could test it later. But how are we doing also? Not too bad. So we would say, so how does this, yeah, okay, I think I understand now. So if, now, what this is looking for seems to be increasing numbers. 5, 6, 1, 3, 2, 7, 5, 6. So this, see, the thing I'm a little uncertain about here is this. I should see. Should see something here. Aha! Thought so. See this 1, 3? This does not show up. I think this is also incorrect, this function. Yeah, that's what I thought. That's what I thought. It works on these test cases, but it doesn't make it clear if the numbers have to increase by exactly 1 each time, or if they can increase by an arbitrary amount. So I think the solution I had is pretty good, because this doesn't actually cover this case. Like if you had 1, 3, 5 here, right? Try that. See what you get. See what you get. Should cover what I'm talking about here. see how we do here. Let's see how we do. One, 3, 5, right? Wrong. We would get the wrong answer here, right? So this will give us different, yeah. So I think actually the answer I supplied is pretty good. The answer that I supplied is pretty good. I don't really see any ones that are that much better. Or at least this one wasn't as good as I thought it would be, the one up top. This kind of only passes the test cases. If the problem was a bit different, this wouldn't work properly. And then there were some others here that I thought were okay. Kind of concise. Yeah, this I thought was interesting. Partition, range, count. Oh, what does this do? You know what I'd be willing to bet though? I bet you the ones that are really concise don't actually solve the problem the way we were expecting. As I've described here, we've got these two test cases. All right, what are we doing here? So, okay. Function S takes this collection, I think. You've got this OR of this thing with empty, okay. This takes the first of a filter, okay. Partial, apply less than. Not entirely sure, I guess this is the filter, so not entirely sure what that does. How does that work? There's a map cat here of a function onto this range. So this range is the size of S, 1, -1. So this is going backwards, this range. Starting from the count of S down to 1, backwards, not including 1. So down to 2. And you're going to partition these values, L, 1, and S. So you're going to partition S on L. Oh, whoa. So, okay, map, and then concatenate all of these values. Okay, so starting from count of S, which is a partition on S, on the size of S, with a step of 1, it looks like. Immediately, I don't think that's a good idea to do that. And then you concatenate all of these things. Oh, this makes it an increasing sequence. Oh, that's interesting. Oh, I see what it does. Oh, this is pretty cool. This is also extremely inefficient, but what this does, it says, this map cat gives you all of the subsequences. So effectively all of the subsequences of consecutive subsequences over S. Give me all the consecutive subsequences, then filter on only the increasing subsequences. And then give me the first. And use an OR if there aren't any increasing subsequences. And this also only considers subsequences of at least size 2. That's what this step 1 does. This range could have gone the other direction too, it doesn't really matter. Yeah, remember I was talking about how you can use the step to create like what do they call that? Intersecting subsequences. consecutive subsequences. So yeah, it just concatenates all of these subsequences into a gigantic sequence of subsequences, and then we filter on that entire thing. Now this is kind of interesting. Let me take a look at this. This doesn't quite do what I think it does. We want this sequence. Alright, if we do this, very curious as to what we get. So we do get all of these. It's every subsequence possible. Size 1 of size 1, 2, 3, 4, 6, 7, size 7, 2 of size 6, 3 of size 5, 4 of size 4, 2, 3, 4, 3 of size, no, 5 of size 3, 6 of size 2, and that's it. Yeah, it's not just quadratic actually. There's a lot of these. Oh no, it's quadratic. It's a quadratic number of these subsequences. And when you apply this filter, this makes things interesting. Okay. I was curious. Yeah, so what this does is so this is true, right? So this has got to be an increasing sequence, and it's being applied to a sequence of sequences. So because it's a sequence, you've got to use this apply, and then you've got to create a partial function out of this, because this apply with this guy is not necessarily a function, but now it becomes a function that you can actually feed things into. So now, right now, we this is kind of clever. So now that we've got this piece, now we know we're only looking at the increasing sequences. And now the really clever thing is he put first here, and this will always get the largest valued sequence and the first one you see. And the reason is because he went backwards here. He started with the largest count. So this first value will always be the largest. In other words, the size of these sequences is decreasing, which we did notice that, right? It starts 7, 6, 5, etc. Kind of pretty neat, pretty clever solution. Inefficient, but clever. I like that. It's good. Yeah, I think when you get to the harder problems, it starts to get kind of like, if you're really concise, then it's going to be probably inefficient. You can still be concise and correct, but not nearly as concise. Like that was a one-liner. It was like very clear kind of clear what he was doing. I wouldn't say it was extremely clear, but relatively clear. Yeah, I would say I do agree. I do think Clojure code is more readable than other languages. I actually agree with that. I think so, because you just kind of follow the the trail, so to speak, and you get a sense of what's going on. Whereas in other languages, like there's so much state involved, there's so much quote unquote other stuff involved around the program that it's really difficult to follow what's happening. Like I have the software that I support professionally has like 2 million lines of code in it, and let's just say it's not that easy to follow what's going on. There's so many things that are going on in there, so many pieces. It's really it's kind of wild. It's actually, when I think about it, it's like dang. It's pretty involved. Yeah, I'm kind of lucky, man. I get a nice little spot in the economy. Nice little place in the modern economy. It's not too shabby. So anyway, that's this problem. It's pretty neat. Let me go on to the next thing. So yeah, I'm not too impressed by the other solutions. I saw the more concise ones because they were like less efficient. Probably won't be able to do this more. What are some acronyms, synonyms for concise? I've been using that word so much. Can use some synonyms. Succinct. That's a good one. Succinct, terse. Succinct is better than terse. Breviloquent, compact, compendious, laconic, epigrammatic. Yeah, not too many of the things are so the breviloquence would be you would sacrifice to make things more succinct or breviloquent. You would need to probably reduce efficiency. It's not great. Laconic. Very few words. Yeah. Okay. And epigrammatic. Okay. Epigrammatic. Yeah, I prefer breviloquence, epigrammaticism, and laconic, concise, succinct speech. Yeah. Breviloquent. I like this a lot. This is a good one. Breviloquent. Give it to me. Give it to me. Concise, breviloquent.
Breviloquent.
Awesome. Epigrammatic, breviloquent, laconic, concise, succinct. Can add these words to my repertoire here. All right. Yeah. Okay. So yeah, neato. Partition and sequence. Okay. Medium, sequences, core functions. Write a function which returns a sequence of lists x of x items each. Lists of less than x items should not be returned. Partition and sequence. Okay. Interesting. So I think I kind of want to take a break and like maybe we'll do this problem and then yeah, take a break. Maybe a couple more problems, then we'll take a break. So okay, partition. less than X item should not be returned. Interesting. So this partition is not going to have any padding involved. How can we achieve that in a simple way? Well, again, you can always use reduce. You can use the same reduce that I was using previously. I created something with a hash map type of deal. Can be done. Sequence of sequences. I mean, you can use a reduction, just like the one that we were using previously. I just kind of prefer not to use that if I can avoid it. I don't know how I would do this otherwise. You can use a reduction with some modular arithmetic and should be in good shape. So, okay. Let's do collection. Let's say we're going to use a reduce function. And this is going to look like two things. Another interior function. That's fancy. And then there's going to be what you return is a sequence of the previous value. Do we care? We kind of care. We want to count. Yeah, we want to count to consider. Could start off at 0. I think it's fine. So we'll take ret and the current value and some v and collection. They all kind of take the same form here. And the way this is going to operate is an if and two things. And those two things, what you're going to want to do modifying a sequence. Modify the back of a sequence. Clojure. Is there a way to do this easily? No. Oh, interesting. Huh. So I'm thinking maybe I don't want a sequence after all. Maybe I'll just do a vector. Maybe I should just use a vector. Yeah, I could maybe just use a vector. It's kind of awkward thing here. I don't know. I mean, you could always convert the vector to a sequence afterwards. I don't know how it's actually implemented. I'm kind of curious what the actual implementation of partition is. Also curious to see what other people did for this as well, because I probably would just do this. So, depending on what C is. Does this have enough battery juice? No, it doesn't. Oh boy. Uh-oh. We back? Hopefully back. I don't know if I can get my phone to charge. Sucks. To charge my phone, I think I need not charge. I don't know. We'll give it some time. Hopefully it charges. Yeah. So what I was thinking was or is a certain if condition, and otherwise, so count. We're always going to increment count in all cases. And we're going to say if we're equal to modulo 0, if modulo the count using, it's actually two values, n and collection, using n, if that's 0, then increment C every time, but also you're going to associate with ret the last value of ret with get or last of ret, and this last of ret we're going to conjoin with v. Yeah. Or add to a sequence. Can we do that? Clojure append to a sequence. Can we do that? So there's differences between sequences and there are differences between sequences and collections. I actually want to do cons v and Kind of interesting. Otherwise, this is cons v of an empty sequence. And this is you append this to ret. Is it that simple? I don't think so. That's definitely not. Unmatched limiter. Excuse me? Where? What? I was not expecting that one. Wait, really? This is going to take me a very long time. I think, I don't know, man. Lisp likes, I'm not super comfortable. I think it's going to be a long time before I really get comfortable with these. Oh, that's why. I see the problem. Probably should just test this locally first. There's kind of no point in no point in testing this inside their editor because it's, oh wow, you're kidding. Whoa. Zero, 1, 2, 3, 2, 4, 5, 6, 5, 7, 8. Oh. Compiled. Did not do what I wanted it to do, but I compiled. That's neat. So maybe we gotta go backwards to this collection. I mean, we can. If we're gonna be using cons here. No, that doesn't seem right. I don't know, man. Well, I mean, yeah. What is even going on? N is 0 modulo 3. Oh, I think it's the other way around. Okay, that's a little bit better. Let's see. Nice. Very close. See the problem though, right? Let's see if we reverse this. Getting close to. And then we gotta reverse the result. Interesting. Maybe we can do it the other way around. We can do like. Maybe we can do. Alright. I want to use a sequence. And I want to say. We're gonna cons ret. We're gonna use. It's gonna be in front. And then we're gonna say, instead of associating ret with this, we're going to modifying a sequence. Changing the head of a sequence in Clojure. Oh boy. Oh boy. Transducers. Sequences, collections, producer, other, sequence in the sequence out, get shorter, get longer, tail items, head items, change, concat, distinct, flatten, group by partition, place, remove, shuffle, restore, compare, process items, map, map, place, secure, queued sequence using sequence extract, first, second, next, last, construct collection, pass to functions, search, force, check for. Oh, I know what to do. Aha. You can cons with last. That works. Didn't think of that. First cons with last. Alright. So let's try that. So so we can say, let's try this. We're going to take the first of the sequence. I'm going to cons with the rest of the sequence. And we're going to get this first, and we're going to cons with this first with V. Aha. How about them apples? What does that look like? Determined to try to get this using sequences. Hey, look at that. Pretty close. It's pretty close. What happens if we reverse this? Oh. Not bad at all. Not too bad. I will take it. I will take it. Although I should maybe try something else. Maybe this is not quite right. Oh, it is not quite right at all. No, never mind. This is awkward. Gotta truncate this before processing or during processing. Man. No. Wrong. Wrong. I don't know, man. I don't know. I do not know. What do we even do here? What do we even do here? Take a break. Take a nice break. Nah. You could truncate the first few values. Like, that's not really a bad idea. We could try that just to get through the problem, so to speak. What you can do is drop count of the collection modulo n. Let's try that. Yeah. Yeah, it seems to be the way to do it. Okay, and then there's even a, after the reduce, you could do a first. So that seems to be what we want. Now what's interesting is, that's fine. I was gonna say you can do like some threading macros here, but it's alright. It's okay. Yeah, pretty much almost always need to take this into the editor when they're kind of involved, the questions. Nice, got them. Cool, very cool. Let's see their solutions. I think we'll stop here. I'm kind of tired. I want to like take a break. Didn't do too many problems. I got a few, maybe four problems. But that's fine. Yeah, everyone's is gonna look like similar to mine. Apparently you can name your function. I didn't realize you could do that. Maybe I should know that. It's kind of, oh yeah, well, I guess I did know that. I don't know. Not sure why. Well, anyway. Loops and recurrences, reduction. I think I gotta really sit and read through these. This is pretty good, I think. I like that one. Note to self, there were much better recursive solutions. Try again. Iterative solutions. Nice. Oh, look at that. That's cool. Or partition by. Oh, that's cheating. Come on. Use partition by. Come on, man. Come on, man. Oh, look at this. Take while, map, take, iterate, partial drop in. Ah, that's interesting. Although I kind of not sure how I feel about this. It's like iterate, partial drop of L. I guess this is okay. Yeah, I guess it makes sense. So when you take, you map this take N and then you drop N. The problem with this though is like, I don't know how many times did the drop iterate over the sequence. Kind of interesting though. Definitely interesting. I like this. Yeah, I really like this. This is pretty concise. So you partially drop a whole bunch of elements and iterate, right? Create this infinite sequence, lazy sequence, and you map take to each of those results, right? Which is yeah, that's fine, I think. Take of n to the result, right? So yeah, okay, I understand. So this will cut into the sequence, and then this will take the first few elements in front of the sequence. You get this map. Now, this is still a lazy sequence. This take while. N is equal to the count of number percent. Now this I don't totally understand. Oh, you keep taking until while n is equal to this, and then at some point after dropping, this won't be true anymore, and so you won't take anymore. Oh wow. Oh wow. Amazing. That's a heck of a solution. That's a good one. I like that. Take a while. Predicate must be free of side effects. Turns the transducer, no collections provided. Oh. Wow. Amazing. So this take a while. Wow. I really like this construction. This is really good. I think it's efficient too because I don't think the drop necessarily is I think it's linear in n, or not necessarily linear with respect to the sequence it's operating on. It's because I think drop is constant time each successive drop. So I think this is actually linear time overall, which is pretty good. It's pretty good. It's pretty good. And some people did similar things where you recurse with F, and you recurse with basically the same thing you did here. Where is it? It's basically this, but with doing it recursively. I mean, this is kind of recursive, but the iterating part is somewhat recursive. Not really though. Pretty neat. I like this solution. Yeah, I think most of the recursive solutions look like that. Alright, so there's ways to do this that's really concise, I guess. More concise, way more concise than how I did it. Most of them seem to be right dropping from the original sequence. I only dropped the first portion. Wow. Let me see, let's go back to the problem. Let's see that again, the iterative one. I like that better. So you iterate, and what you do is drop. So we'll have a function. Take n in columns, a collection, and what we're going to do is iterate over this collection. We're going to iterate drop n values from the collection, and then what we're going to do is we're going to map a function which will take, I think we can do this. I don't know if we need to make this an anonymous function. So you've taken and drop in, right? And we map we map this taken over each of these solutions, and then we're going to take while. This is what we take at the end is now this we can do anonymously. Count of this is greater than 0. Actually, it's got to be exactly equal to n, right? So this portion that we take, if it's equal to n, then we do that, right? And this take while gets another piece. So we get this once for iterate, once again for map, once again for take while, and finally one for function. Wrong number of arguments. Has to take. Interesting. Create a partial, I think, right? That's an alternative instead of creating a instead of creating a anonymous function, you can just create a partial. Both of those work. Oh, that's pretty cool. That's very concise. I like that. I like that a lot. Man, why don't I think of these things? Why don't I think of these things? Shoot. Shoot. I think that was me. I think it was me. Alright, let me get out of here. So, thank you all for watching. Talk to you all soon. Have a good rest of your night. I want to go to sleep. I'm tired. Next problem is count occurrences. We'll come back to this. I think, yeah, I'll probably go over a bunch of stuff. Probably at work. I'll probably work through a bunch of these problems and come back and review them afterwards. We got about 100 more problems to go through, so we got plenty of practice we're gonna get here. But yeah, man, we'll get more and more familiar with Clojure and like how to write, breviloquent and correct, efficient, and breviloquent functional code. And I imagine any other functional programming language would have the same kinds of constructs. Yeah, so this will be interesting. So yeah, take care.